Good morning, everyone, and good morning to the virtual conference. This has been a very interesting endeavor on the part of ACEC and Roads and Streets, but we're making the most of it. I'm going to ask you to please send your questions through the chat to, and then we will answer all the questions at the end of the presentation. If you'll allow me to please introduce our speakers today. We've got Matt Hemseth. Matt joined Archer Western in 2016 to serve as construction manager of the $492 million TexRail commuter rail project in Fort Worth. It's helping to establish the first commuter rail connectivity between the city of Fort Worth and the DFW International Airport. Matt earned his Bachelor of Science in Mining from the University of Nevada, and he spent 13 years building and managing transit projects, including Line Section 1 for Valley Metro. He's currently working on the DART $892 million design build in Dallas as the senior project manager. In his spare time, he operates a small farm in Joshua, Texas with his wife and 2 children. Doug will also be presenting, and he's a graduate of Purdue University. He's a Boilermaker, where he majored in structural engineering with 18 years of heavy civil construction experience. He is currently serving Archer Western as design build manager on Matt's Silver Line project in Dallas. And prior to his rail work, Doug was a project manager for Walsh on complex bridge projects throughout the Midwest. He has a passion for bridge building. He's worked closely with the specialty contractors, engineering consultants, railroad entities, and owners reps involved to deliver the complicated hole-in-the-wall section of today's presentation. Doug lives in Flower Mound, Texas with his wife and his twin sons. With that, I'm going to turn it over to Matt.
All right, thank you, Pam. And to get going on this presentation, again, this is the accelerated construction of the TexRail project. The first few slides will go through the rest of the project, what it is, what it was, and what we were tasked to do by TexRail. So going on to the corridor, like Pam said, this is from downtown Fort Worth. For those that are familiar with the DFW area, Fort Worth is on the west side of town, Dallas is on the east, and DFW Airport is right there in the middle and one of the largest hub airports in the country. So what we were tasked to do is to build a commuter line from downtown Fort Worth connecting to DFW Terminal B. Through there, we went through a few cities. We have 6 stations in there. And what we're going to talk about today is primarily the bridges and a lot of things that we had to move. But getting into the numbers a little bit more, it's $495 million CMGC job, 24 bridges. We'll talk about 4 of them here today. 39 grade crossings, 13 jurisdictional authorities, which included the airport, Union Pacific, and some of the other major rail players in the country. And then just a lot of scope of work with excavation, retaining walls, and utilities. So next slide, why CMGC? And there's a lot of assumptions, especially in this job. As we get into the hole in the wall, you'll see all the assumptions that were made beforehand, and with assumptions come high risk. So bringing an Archer Western Herzog onto the project early, TexRail was able to mitigate some of those design risks and construction risks. So during pre-construction, we had a 15-month pre-construction, and that was able to help us review and optimize the design, specifically hole in the wall, as well as a couple of these other bridges. So as we got into planning the work, you got to be concerned about what the other agencies and railroads are going to require. And for hole in the wall, shoring was a major component as we were going under 4 active freight lines that go through Tower 55, one of the largest and most congested freight crossings in the country. Schedule-wise, this was a 24-month from NTP to be able to build the work. So Doug, on next slide. So schedule NTP for substantial completion So what that meant is we had to build over a mile of track per month to be completed. In this picture here is one of the major river crossings we had to do that is also included in the 1 mile per month. And all of the other design challenges on a CMGC job. We had over 200 contract and drawing revisions to the project. So very complicated, very complex job that required a lot of coordination from the designer, the owner, and us, the constructor. So to be able to make that happen, we had to use multiple forms of accelerated construction. Most of these had to do with bridges, but the next one we'll talk about is at-grade track. So there were 17 miles of track under existing freight that had to be completed while keeping the freight open. And the freight allowed us 3 and 5 day outages every week to be able to get those 17 miles done. Some of the more complex areas, we were able to get 400 feet done. And then some of our longer shutdowns, we got up to about 2,000 feet, and those were done in a 5 day outage where we removed and replaced the track in its entirety down to the subgrade and back up in 5 days. Next. So coordination is absolutely key when we were working with the Fort Worth Western Railroad in these outages. We had a very detailed schedule, what happened every day, overnight, what scope was supposed to be done. And that way we could adjust as we needed to be able to bring crews in early, or if things were getting delayed, that we'd be able to bring in additional resources to make sure we hit our closures. And out of all of the outages, there was one instance in the 2 years that we missed our outage. And the reason is we got about 3 inches of rain right when we opened up the grade, and dirt and the grade didn't mix with the rain very well. So that one was a little tough, but overall the team did a great job and overcame those. The picture coming up next, this shows portion of the hole in the wall. This is part of the track demo. Very congested, a lot of work going on. And again, this is a three-day outage to get some of this track work done. So being able to get our materials where they needed to go, short work windows, limited access, and weather, all were key challenges and key planning aspects to this project to be able to make sure that it went off without a hitch. Next, Ira E. Woods Bridge. This was a 90-foot through girder bridge. The Ira E. Woods is a historic bridge, and where it was situated on the job, there was no adjacent property to be able to build the new bridge close by. So we actually had to build the new bridge approximately 2 miles away in a laydown yard. And then we drove the new bridge down Main Street in Grapevine to its new location. So the picture here is the bridge coming to its final resting place after we moved it 2 miles down the main road. This was done in a 5-day outage. And then to make it even more complicated, the old bridge we had to take and move it about a mile down the road, and it's now used as a hike and bike bridge there in Grapevine. So a lot of bridges moving down the highway or down the roadways there. So not every day you see bridges just moving through the city. But to make that happen, when you're moving bridges of this size, underground utilities are a very major concern. So working with the city of Grapevine there to make sure that we didn't impact any of their water lines, because when they're only 4 feet deep and you're moving almost 1 million pounds down the road, a lot to be worried about there. The existing bridge, and all old bridges, as everybody is aware, has all the environmental concerns with lead paint and asbestos and all that. So being able to get that moved and abated. Major traffic interruptions. Again, this was the main roadway in and out of Grapevine, Texas. And then building the new bridge substructure had to be done in advance of tearing out the old bridge. So in this picture on the left-hand side, those steel plates are actually covering the new abutment. So we had to dig out to get to that new abutment to be able to set the new bridge, and very limited access. So what you're seeing in that picture there is exactly what our access was and our entire right-of-way. Next picture. This next bridge, Big Fossil Creek, this is going over an existing golf course. So there's a golf course down below, and Big Fossil Creek goes in here. To be able to get here, there was absolutely no way to move it up and down the rail. So our team elected to do a horizontal slide into the permanent alignment. So if you go to the next slide, Doug. So to make that happen, the bridge was already designed to accept the existing or the new bridge in its final location, but to be able to build it, we came up with an option to just extend the pier cap over so we could build directly adjacent on the structure that we'd be setting it on, and then use Tillman rollers and rods and move the bridge horizontally across the cap into the final location. And again, this was in a 5-day outage. If you go to the next picture, we'll show more of the tight access and what we had to deal with. So on the right-hand side of that picture, there's some high transmission power lines, so we couldn't swing around getting into it. The only way to get those beams into place was bring them by current or by rail to the cranes, and then the cranes were able to set them down onto that new cap. And then from there, we moved it over to the new location using Hillman rollers. So the challenge is here, public golf course, and being in Texas, they don't shut down very often, maybe shut down a little bit more than they do in Phoenix, but still don't shut down at all. 5-day rail outage here, and what made this one even more challenging is you can see the steel beam there in the middle. Well, the 2 outside spans also had to be replaced in 5 days, and those were box beam sections. So being able to get the old bridge tore down and a new bridge erected in 5 days was very, very difficult. Our original schedule was 9 weeks, and the team did very well. It did rain on us a little bit here, but we ended up getting done in 4 days, so even 1 day in advance of our 5-day outage. Next bridge was 28th Street. Again, this is a bridge that required freight to be able to go over it a few days after we were done. So being able to build this one off to the side, this was also a 130-foot through girder span, and used SPMTs on this one as well. If you go to the next slide. So this one, a much larger bridge than the Irie Woods Bridge, but being able to get it off to the side, we were able to get all the welding done. This 28th Street is a TxDOT owned roadway, and they would not allow us to close that road for any length of time. So to be able to get this entire bridge welded the way it needed to be, we had to build it off to the side and then just do our touch-up welds and final welds once it finally got in place. And then also to reduce the impact to the Fort Worth Western and the Union Pacific. So this is that area there. We built the bridge just off to the left-hand side by that crane that's white. We came down onto the roadway and moved that bridge into place. And again, this was a 5-day outage. The other thing we had to worry about in this area, and it goes to an archaeological site there on the right-hand side of the picture, is a cemetery, Mitchell Cemetery, that dates all the way back pre-Civil War. So very sensitive area in terms of archaeological sites. Had TxDOT and freight railroads, so very, very congested area with a lot of jurisdictional authorities. And then the overhead and underground utilities moving that bridge, we actually had to raise up a couple of the overhead utilities to be able to make that bridge fit in its final alignment. And with that, that's all the boring moving stuff. Doug will take it over from here and go through the hole in the wall, and I believe that's what everybody got on this call to actually learn about.
Thanks, Matt. So I think you heard Pam say at the beginning, I'm kind of a passionate guy for bridges. I'm a bridge nerd, if you will. And this job was a bit of a dream for me to be able to be involved with, because this is a really unique thing that we did on this project. The project was full of bridges, and what we're hoping you would take away from this presentation today is on these railroad projects. A lot of people in the audience, I'm sure, deal with DOT projects, maybe more than rail, but a lot of times you have those freight rail interaction on your project, and we were hoping you could see some ways that you could maybe take a second look at some of the planning for in advance of those projects, see how to get them done a little bit faster, a little bit safer. Safety and high quality is what it's all about when you're dealing in any construction setting. That's what we ultimately were after on this job. So the hole in the wall, it was kind of a colloquialism, if you will, but that's what it's all about, is that picture right in the middle of the screen. You can see the little window that the Trinity Railway Express shoots through, as well as Amtrak and Union Pacific Railroad. There's a lot of crisscrossing of other infrastructure over the top of it. And essentially what we had to do in this portion of the project was get rid of the old span there in the middle of the sandwich and replace it with a brand new one. And we had to do that all under short outages and not disrupting freight service or passenger service or TxDOT traffic. You can kind of see in the background picture there, there's a major thoroughfare there into the middle of downtown Fort Worth, going over the top of this interchange. So when they brought me on this job, this was the first piece of paper I got to look at, and kind of jokingly say this is not a joke. When I took a look at this, I honestly couldn't figure out what we were building. So I'm trying to break it down for you easily here with some markups and some red lines. So you can see the line work there is basically the future TexRail track that we're trying to run underneath all of this through the hole in the wall. Off to the side, we had to shoe fly BNSF over to the side. So basically the tracks that go over the top of what would become the double track TexRail corridor is shared by UP and BN over this kind of yellow looking shaded bridge here. So we moved BNSF over to the left-hand side of the screen on a shoe fly bridge while we replaced the old bridge in the yellow shading. And then just to give you an idea of how tightly packed in we were, all that work in the green and yellow shading had Spur 280 over the top of it, major TxDOT thoroughfare into downtown Fort Worth for commuting traffic. So here it is in Google Earth view and some KMZ layers. You can see the TexRail alignment that was coming through here. Peeling off of the TexRail alignment is Amtrak trains. UP uses a portion of this as well. You have Trinity Railway Express coming in on the existing track. So here are kind of all the players. I'll just highlight them on the screen here as we go. So you have Trinity Railway Express, Union Pacific, Amtrak, BNSF Railway. So you can see it's a very crowded party, and we're all trying to function together. And then you've got TxDOT over the top of everybody. So there's the KMZ line work of essentially what we were building underneath everything. So sometimes the old-fashioned way is the best way, and that's what we did here. We had a guy that enjoyed making architectural models with an X-Acto blade. If there's anybody old school in the crowd, you remember doing these things. This is kind of how it used to always be done before the days of 3D and CAD. But this proved pretty valuable in a lot of our meetings, as we were able to take off layers. We actually had the TxDOT highway going over the top of this. We were able to take off layers and show everybody step by step what we'd be building. That helped us hammer through some of the problems as we went. So the picture on the screen here illustrates the headroom challenges. This is the Trinity Railway Express track, which would become the double track TexRail commuter track. This is sitting up on top at the same grade. The crane you see here in the picture, this is at the same grade that all the freight railroads were passing underneath the TxDOT overhead. So you can kind of see it's just like stack upon stack upon stack of things to work within. And that's the type of headroom challenge we dealt with all the time, drilling shafts and, installing formwork and placing concrete pumps, everything you can imagine that goes along with a construction infrastructure project. So Matt talked about constructability reviews and CMGC. After constructability reviews, we went through this with the owner's design. So the owner's design had a really complicated kind of detail of underpinning an existing TxDOT support, offsetting some columns, and it was going to be kind of a big mess to build. So we brought in a third-party construction engineer and a lifting consultant, a heavy moving consultant. We had Mammut on this project. We had another company called Burkhalter, which is now branching off and doing a different company. They're not Burkhalter anymore. But in any case, we use heavy lifting equipment, SPMTs, push-up systems, and I'll show you all the details on these things. But essentially we had to replace a bent cap on the existing TxDOT overpass in a very short one-time railroad outage. And then we had to pre-assemble our steel bridges off to the side, the new freight rail bridges for UP and BN, and then bring those in under 2 separate short outages. It was phased construction, so you could keep all the freight moving while you're building all of this. So very tightly packed spaces. A lot of times we're building in between UP on one side of us and BN on the other side of us. So it's very busy and a lot of planning as a result. So this gives an overview of the push-up system that we used. You can see the stacks of barrels. These are 1 meter high each. So the way we conceptualized getting rid of the old pier, but essentially down here it was a single track corridor. We had to widen it out to a double track. So you'll see some views of the existing pier, and what we were doing was lifting the 280 overpass off of its existing bearings so we could get the old pier out, put a new bent cap in place on a straddle, and then drop the deck back down on top. So just the step-by-step of how this worked. Schematically here, you see this is the existing pier cap going across a narrower straddle bend, I'll say. This is a schematic of that blue thing you saw in the previous view, which is our temporary cap that had a jacking system on it to lift the existing bridge off. Once it was lifted off, you could demolish out the old structure while you keep it supported on the temporary bolster. Then step 3 was to fish this new, larger section, longer straddle cap underneath the existing TxDOT bridge. And then you take all your temporary, you basically transfer the load over to the new bearing and take all your temporary shoring down. So some pictures of what we were doing here. Off to the bottom hand side of where you see the crew there laying out the foundation of this tower was active Trinity Railway Express track. Also had Amtrak on it once a week, UP a few times a week. And then but basically where I'm standing taking this picture is the shoe fly bridge that BNSF would go across pretty much all day long. We had a freight train rolling by us on about an hourly basis. Sometimes they would park and switch car. This is a place where they had multiple tracks and crossovers to where they could switch cars on and off. So you can imagine just tons of logistics, tons of communicating and coordinating with railroads and with everybody. So you see the stacks going on. So basically you stack this shoring system up until you get it up close enough to the bottom of the existing deck, and you put this jacking cap on. This jacking cap it's designed for multiple uses. You can see there are kind of pin connections here, so they could swap out this center section to make it narrower or longer, whatever they needed. So once you get it to the bottom of the deck, you put these bolsters on, and then you incrementally jack the 280 deck off slowly to get them off the existing bearings. So this is a big spot where our third-party construction engineer came in. We hired McElhaney, if anybody's familiar with them. And what McElhaney was able to do was model the stiffness of the existing composite deck and figure out that when the deflection started coming out of this blue jacking beam, they fine-tuned the shim detailing that's on top of our jacking stools, so we wouldn't have to be going over here and filling some shims an inch and then running over here and chasing it from location to location. It worked out really well. McElhaney did a great job, and we spent a minimal amount of time up here on top of the tower putting shims in place, which was kind of the goal of the whole thing. So let's see, get to the next one. Okay, so this is a little schematic on how all this was done. So if you can imagine, in the background of this picture, our temporary shoring tower was behind what you see here shaded in red. What you see shaded in red is the existing steel bent cap. We had some custom rigging devices fabricated, load tested, designed, signed and sealed. And then we had a couple of cranes sitting off on the outside of this to lift this off of its existing columns. And again, this is after the temporary shoring system had taken the load of the deck above and daylighted it off of the bearings. So you remove the cap, and then we did a wire saw cut of these existing columns to get them out of the way, just enough to be able to put the new bent cap on top. So what you see here in the dark line work on the outsides is the new straddle cap columns to allow a bigger span underneath. So you can see the shaded that's going to be coming down is narrower than the new. You got a single train down below, and when we're all done, we're going to have two. So the blue shaded box is our new cap girder that was stuffed underneath. I've got a little bit more to show you on how that was done. But if you can imagine, then this blue cap were placed up top of the existing, or sorry, the new straddle columns, and then the load was taken out of the shoring system and down onto the permanent bearings. Really tight working quarters again. This time, headroom got the best of us. We had to come up with a way to go up and over the top. So we had a 600-ton crane out here, a big hydro, reaching up and over the highway. So this was a nighttime outage of the highway, dropping the block through a 4-foot gap, essentially, to be able to maneuver one side of this new pier cap. You can see a rail car here in the foreground. So we utilized our shoe fly bridge, our temporary BNSF bridge, worked with the railroad to keep them off of the one track we needed, brought the new cap in on a rail car. Well, first of all, took the old cap off, landed on a rail car, took it down the way where the new one was sitting, flipped them out, brought the new one in, and lifted it up and on. So it was a really efficient operation and highly coordinated with railroads to get everybody rowing in the same direction, as we like to say. So here's our wire saw operation, cutting out the existing columns. And then probably my favorite thing of this whole job, I've been around the block a little bit and seen a lot of lots of tools and tricks of the trade. But this is a counterweight offset picking device. In the steel erection world, we call these a pump handle, because if you can imagine yourself pushing down on that back end, it's like you're operating a pump handle. So this counterweight would trolley back and forth through a remote control that's held by an individual on the ground. And as your crane comes up on the piece of column that you cut out, you keep moving this trolley back and forth until you get it perfectly balanced, and then it picks it right off and you can swing it out. So you can reach up and under something. It was a perfect application for all the headroom issues that we had. And then the success of this operation, so we had a 5-week outage that was talked about in the owner's original concept, where we said, you know what, if you let us do it our way, we can make this design a lot cleaner. We can bring it in an operation that's much more efficient. So we ended up, after negotiations of our redesign, at a 43-hour allowable outage, and we finished it more than 20 hours early. So we were really pumping our fists at the end of that one. We felt pretty good about ourselves. And then we got a dose of reality, because this next one was pretty tough, but it went off really well too. But I'll share some of the challenges of this. So after the pier cap, actually it's order-wise, we did the bridge first, the pier cap second, and then the second phase of the bridge. But this is better order to show it in, so you're just going to have to roll with it. So for the steel spans, we rolled them in, as you saw on that previous slide. I'll go back to that one. You can see in this photo, we have the new bridge on an SPMT coming in on a temporary runway, which is bridging the hole in the wall, as we call it. There's a temporary gantry system underneath that jacks up and lifts the bridge off of its temporary temporary platform. And then we pull this runway out and drop it down into the hole. So the roll-ins is kind of similar to what Matt talked about earlier in the presentation, with the close coordination between us and railroads and other stakeholders. We had this on an hour by hour by hour schedule, all the way from the beginning to the end of the outage. We had checkpoints. These green things are basically quality hold points, because there's certain points of no return, if you will. Anytime you do a complicated operation like this, it's paramount to say, okay, we can't screw this up, and we can't screw this up, and we can't screw this up. And those are the hold points, right? So we identified all the hold points in this case and walked the railroad on an hour by hour meeting. We said, okay, hour 1, we're going to do this, 2, we're going to do this. And then there were check-ins throughout the night on a text message string, basically to say, you know, we should be at hour 11 and we're at hour 12. So we're trending an hour ahead. Actually, at one point we were trending like 18 hours ahead, but we told everybody we were on time. So we get everybody too excited and then have a hiccup happen and it all go blow up in our face. So how we were able to get this accomplished. So I mentioned we had a temporary runway If you can imagine, you're looking through the hole in the wall, basically, where you see this gantry system. So we had a gap here between new abutments that was much larger than the gap between the old. You had TxDOT running over the top of us, of course, and you had active freight on either side of us running back and forth constantly. So step one of this operation was to launch this temporary runway across the gap we used basically a winch system. This is just a big heavy-duty tow truck, and pulled this runway in. You can see it supported on temporary supports on the right-hand side of the screen there, on rollers, and basically it just rolled across the hole until we landed it on the opposite abutment, basically created a temporary bridge for the new span to ride up on. A challenge of this is how this gantry system was detailed. You can kind of see from the center of the screen here, we had an interior gantry system that was used to support this runway temporarily as it came across the hole. Negative moment got a little too high when the thing deflected down over a certain distance off of this last support at the abutment. So we had to temporarily support it with another roller in the middle. So that's the highlighted gantries you see there. And then once the system were over that temporary support, we'd jack it a little bit higher to allow a little bit more deflection until it landed on this other side. Some pictures of that. So here's the hole in the wall. Basically, we're bridging the gap of the hole in the wall with the temporary runway. This is the temporary runway being launched across the hole, and the gantry grillage there with the rollers on top to accept it, to keep it from getting too deflected for its own good. And then our pre-assembled span was about an 800 kip load. Put that on a self-propelled modular transporter. SPMT is what we refer to that as in the industry. And then we rolled that up a temporary ramp over the hole, basically into its final horizontal position over the supports. And then the exterior gantries that you see here shaded in yellow of the 8 gantry system would lift up on lifting beams that kind of tough to see, but it's just above the SPMT wheels. There are 2 beams there that this gantry system would push up on. And so now you can see the span levitating above the SPMT. It's not really doing that because their gantry's holding it. I just didn't draw it that way, sorry. And then the SPMT backs its way out. And then we reverse launch the temporary runway out the other way. And basically what it does is it leaves an empty hole for us to drop the bridge down into. So the pictures we have here is the SPMT system going up the ramp onto the runway. I'm still to this day just amazed how much this ramp deflected when we put it under this load. Second phase, we put a stack of crane mats under this just because one of those things when you see it, your stomach kind of flips, and it checked out by calcs, but we felt better if it didn't deflect like that. So we remedied that on the second go around. And then on the right-hand side, that's the gantry system fully supporting the span completely off of the SPMTs. You can't really see it in the picture, but the SPMT is starting to back out. It's backed out about halfway at that point from where we had it when we brought the span in. So some of the challenges we dealt with here, we had to be careful not to max out the height of the gantry system. Had a 20-foot total stroke, and I think we were something like 8 inches from having it fully extended to as high as it would go. So the detailing of things of the temporary support members had to be just right. If we ended up making things a little too tall and having to push it too high to get clearance above the SPMT, we'd run out of gantry stroke. So that's just some of the things when you do a detailed operation, you think step by step, it's got to be perfect. The skewed geometry of the bridge made it really difficult to design the gantry system for stability. So if you look at the screen here, you start to see some of the geometry challenges. We have a center line of bridge that was different than center of gravity of the SPMT system and the ramp. So that had to be accounted for in the stability of the gantries. Are the reactions going to result in something stable? So here's a quick look at a model. We had to model the stiffness of the composite section very accurately. Otherwise, we would risk overloading one of the corner gantries where you'd have, so like over in this corner, you've got more load to deal with than this corner. And it was also a big concern that the thing wouldn't be able to lower at exactly the same rate. But all 4 gantries were operated separately, so we were able to control that as we came down. and keep an equal load in each of the 4. So that was really key to the operation, is that we had a really good gantry operator. And then step 3, lowering. It's pretty simple on the surface. Mainly what we were dealing with here was clearances. So I've highlighted our lifting grillage, and you can kind of see existing abutment on the right-hand side. The old hole is much narrower than the new, but that had to stay in place to support the existing bridge that was still in the background, carrying UP trains back and forth while we were doing this work. So we had to check lots of clearances with very tight tolerances. You can see some of the things that we had to be careful of. We were going to clear our launch roll in on grillage with our lifting grillage as we came down, because it would basically swallow it. The existing back wall, we were out there on some night shifts doing some extra chipping just to make sure we had enough room. And this is really what it was all about. At the end of the day, when we set this thing down to get the railroad to accept the bridge, we had to be within ARIMA geometric tolerances of a 1/2 inch horizontal, 1 inch plus or minus longitudinal. You can imagine how tough that is to drive something that big in and get it that accurate. But the way we were able to do this was with some laser survey equipment, basically plumb laser, shooting down on a control point. This is where we were before we made our fine-tune adjustment. So we were pretty proud of how close we were able to become. This is how close we were able to get before actually making the final adjustments. And then we made the final adjustments with just chain come-alongs, kind of wrenching the bridge one way or the other, and use the flexibility of the gantry legs to allow us to do that. Since the gantry legs could handle the bridge unbraced, it made it possible to do that. So end of the day, project was very challenging, very exciting. We were all proud to be a part of it, proud to deliver the project for the city of Fort Worth. And I'm going to turn it back over to Matt. Appreciate everybody listening to me. I love talking about this job, in case you couldn't tell. So I'll give it back to Matt to bring you home.
Yeah, so like Doug said, this was a very challenging job. There were a lot of people, especially at that hole in the wall area, that were key to making this happen. The Union Pacific was highly involved. BNSF was highly involved. Rail Pros is the BNSF and UP reviewers. TxDOT was involved. The city was involved. So just an all-around heavily coordinated area. But all that to say that the first train was on time. We had happy mayors, happy owners in the picture here. CMAA Project of the Year, Bob Balser on the left. He is now the CEO for Trinity Metro, and Richie Thompson on the right as resident engineer for the project. Other awards we got: a local RHCA, which is the Regional Hispanic Contractors Association Project of the Year. We got that here a couple years ago. And then probably one of the biggest one is the AGC Build America Award that Clayton and Craig, there in the middle of the picture, went to Denver to accept on behalf of the project. So overall, a very good project. A lot of high caliber awards were on this job. And then that helped us parlay it into the job Doug and I are currently on, and going to be extending this exact same style of system for Dart, continuing to the east out to Plano. So with that, we want to thank everybody for their attention and attendance. Doesn't look like we have hardly any questions in the Q&A, but we do have a few minutes here left. If you can get them in here quickly. If not, go to the booth and get your questions over to Pam, and she can get them to Doug and I to answer any of your questions. And again, that, thank you for your attention and time listening to our presentation.
I do have one comment before we wrap up. You guys have done a lot, so I'm voting for the hole in the wall to be the 8th wonder of the world. And just for the record, I used to live in Grapevine, but I don't live there anymore. But this is very exciting. So you guys can retire now because you've done a great job.
Tell my wife. Today's my last day.
Okay, well, thank you everyone for attending. Again, send your comments or questions to the chat room or stop by our booth, and I'll make sure that Doug and Matt get your questions. And thank you very much for coming.